Okay, so welcome to this edition of the Computability and Application Seminar. So today is a great pleasure to welcome David Belanger, who is going to talk about maximal order types of well-partial orders. So as a reminder, please mute yourself unless you want to talk. And of course, the speaker shouldn't mute himself. So please start.
All right, so what I'm going to talk about today is some joint work we've been doing with Andreas Weiermann. And one thing I want to emphasize from the beginning is that this is work in progress. So it's not perhaps exactly the same as the final version we hope to have. But it's a good start, and I think you will enjoy it. Another thing I'll say is that it's not really totally within the scope of the subject of the seminar, which is computability, of course. But again, I hope you'll enjoy it. So the basic object we're dealing with is called a well-partial order. Now, not everyone has seen well-partial orders before, so I'll just tell you the definition or a definition. It's a partial order in which there's no infinite descending sequence, that is, it's well-founded, and there's no infinite anti-chain either. And this is anti-chain in the sense like this. The elements are not comparable with each other, as opposed to, for example, the concept from forcing. And this has a number of well-known equivalent formulations. Hold on, where's my white? Two that may be of interest, or two formulations that may be interesting. Our first one that uses something called bad sequences, and one that says that every linearization, that is, when you extend the partial ordering by adding new relations, every linearization, adding new relations until it's total, that is a well order. And there are still more equivalents, but the gist of it is that it's sort of like a well ordering, but it's not total. And there's a related notion called well quasi-order, which is almost the same thing, which I might call them by accident, but it's the same thing, except it is missing the relation or the axiom of antisymmetry. But they're, in most cases, the same thing. In most cases, the same things are true about them. Okay, so there's some very basics of the objects we're looking at. Here's some more basics. There's a notion of something like an embedding between two orders called a quasi-embedding. But whereas with an embedding, normally you would expect A to be less than B if and only if the image is less than the image of B. Here it's only going in one direction. And I'll just emphasize that it's actually not the direction you're most likely to expect, it's the other way, from the image to the domain. But it's sort of half the conditions of an embedding. And then this theorem is the first thing you would use this concept for. It's what we'll be using these quasi-embeddings for later. And I left some space here just so I could, maybe try and draw an example of what it's for. So if the codomain of a quasi-ordering is well partial ordered, then the domain is 2, and that's easy to prove. It's not our topic for today, and this is an old well-known theorem. But if you wanted to prove it, you would use these bad sequences. It's approximately one line, and one line that we'll just skip. But if I wanted to give an example of what this is for, I would draw one partial ordering called A. and a second one called B. And how do you define a quasi-embedding from A to B? Well, there are, of course, multiple different ways. But here's one possible mapping. I'm going to give, maybe call them Roman numeral 1 and 2. These ones map maybe to here. There are different choices you can make. But you can check that this mapping matches the definition of quasi-embedding, and then as a result of the theorem above and the theorem below, since B is a well-partial order, well, let's not get ahead of ourselves, since B is isomorphic to a disjoint union of two well orders, actually, it is well quasi-ordered. The theorem below is straightforward to prove, as is the theorem above. Thus A is, whoops, see I did it, well partial ordered. Thus A is well partial ordered as well. Now this is just a beginning example. No one in real life was ever wondering about this, whether it's well partial ordered or not. I think it clearly is. But the general pattern is this, that we have something messy on the left, and we reduce it to something less messy on the right. In this case, just a disjoint union of two well understood ordinals. So that is the most basic tool for proving something is well partial ordered. Now, in the literature, you'll see people calling these two things constructors sometimes, constructors for well partial orders, because oftentimes when you have, when you want to build one, you build it this way, just like we build B. Here's a third constructor called the Higman ordering. Now, the way the Higman ordering works is if you haven't seen it before, you'll at least remember this star maybe is the Kleene closure for finite strings. So what we're doing is we're using finite strings as the domain of an ordering, taken from an existing ordering A. And then we're also equipping it with its own ordering on the strings, which may be a little tricky to parse. But if I just say it in words, it's like the substring ordering, except over here, you would expect this to be equality for it to be a substring. Instead, it's less than or equal to in the base ordering A. So I don't know. This may be easier to explain through examples. Let's say, take 3 as the ordinal. This should be ternary strings. 1, 1, 1, 1. I'm just going to write some things that it's less than 2, 2, 2. 1, 1 is less than 2, 1. 1, 1 is not less than 2. 1, 0, 0, 1 is less than 1, 0, 0, 0, 0, 0. I don't know if this is enough examples to make it clear, but you can see that this one has to go to this one, and this one has to go to this one. But there's some choice in how the zeros are arranged. Okay. So the thing that makes it Higman, I suppose, is the lemma, which is that if A is well partial ordered, then A star is as well. Now, there are a number of proofs of this in the literature. And we're going to see one a little bit later, which I'm uncertain to what degree we can claim it's novel, but it's certainly a little different in the way of looking at it than other proofs I've read in the literature. But for the moment, I think we have some more basics to look at first. Now, what we have, I'm going to draw this dot here in black because we'll be drawing white and black dots in a moment. So I don't want this one to be black. There are different notions of what people have been calling a tree constructor in the literature. There seem to be a few different versions. And in most cases, it's kind of hard to pin down a nice definition that also is intelligible. So let's take a look at, instead of a definition, some examples of how it should behave. And then the definition should come out of that. So, and again, there are different ways of writing this. Some people might just write tx times x, which is certainly more aesthetically appealing, but I like having the dot here. Okay, enough about me. Let's talk about the elements of this tree class, as some would call it. There could be a dot. That's what is symbolized by this singleton dot over here. Or you could look at this side of the disjoint union, which will signify with a white circle. Then X is either, in this case, a dot, or in this case, an ordered pair. So, yeah, that's all the elements. And there's an ordering too. We'll get to that in a moment. But for now, an example would be, I don't know, something like this. So it's a term in something like an algebra with these two functions, a unary or a zero-array function and then a binary function. And as you probably know, you can look at this. I'll draw a squiggly equal sign. As a parse tree. So this tree class, so-called, so named, would be the binary trees. Now, binary trees can mean different things depending on the context. So we really do mean that every node has either 0 successors or 2 successors. And the left and right, whether it's left or right matters, but more on that in a minute when we get to defining the ordering on such T's. For now, you know, I'm not sure why I decided to put these in order of decreasing complexity. We'll see if it was a smart idea or not. But again, here we have two alternatives. Either it's the dot, or, and again, we'll use the circle to represent going to the left-hand alternative, and a pair of AX. We'll call it X1 again, like up here. And A is from some fixed set A, some fixed ordering A, in fact. And X1 is back from that X. What's an example of this? Well, dot is an example, but besides that, dot, circle A1, circle A2. This is sort of a generic version. And what is that basically? Well, the circles don't matter, and this dot doesn't do anything really. It's like the string. And this third one, I'm sure you can do it with your eyes closed by now. Its elements are either the dot or a recursive call, let's say, to this x, and then a shorter string x. And in general, all the elements look like some sequence of these circles representing going left, and then one final black dot. And what did this look like? Well, the only thing that matters is the number of circles. Let's say it's n times. What this looks like to me, at least, is the natural numbers, defined as 0 and successor. Okay. And then the question is, what is the order going to be on these things? So here's how it goes. X is less than x prime if either x is a dot, 0 is less than everything, or x is a successor, x prime is as well, and altogether x1 embeds into x1 prime. And then you can check carefully, if you want, that this is the usual ordering on the natural numbers. It's just a structural induction on the number of structural induction on the complexity of the term, and it works. And then if you write something, again, a little bit messy, like down here, maybe you can predict what the ordering is going to be on these strings. X is less than x prime dot. Circle with a x1, a lower complexity x1, and x prime is as well. We'll call that a prime, x1 prime perhaps. And oh yeah, there's going to be a squeeze. Either x already goes into x1 prime. So the first element of this string didn't matter because it's a substring anyway, even without it. Or in a greedy algorithm sort of way, we can assign A. We can match up the first elements of the two sequences, and x1 is less than x1 prime. There. And again, you can check carefully, but this should be the same as the Higman order. And then, well, first of all, so what we have is a type of constructor that subsumes this previous Higman constructor. We don't really need to talk about Higman orderings anymore if we have this thing around. And finally, ordering on trees. If x is the dot, or x is X is not a leaf node, and X prime is not a leaf node. And either X goes into X1 or X goes into X2. Oh, excuse me. On the right-hand side, it goes into the other one's left subtree, it goes into the right subtree, or both subtrees match up. Okay. So this is known sometimes as the strong embedding. It's far from the only embedding on binary trees or trees of any kind, but this is the one that's most of interest in this context. For example, it's the one that's used in Kruskal's theorem. Okay, so everyone is seasoned experts on how this T normally works, right? Good. Because we're not done with basics yet. Here, there's another object we want to talk about, which is called the maximal order type of a well-partial order. Now, it should be clear that every set of ordinals has a supremum, good. And if you look at the set of all order types of linear extensions, that's a set of ordinals. So it has a supremum. But why are we calling it M of A instead of S of A or something for supremum? That's because, surprisingly, for me at least, that supremum is always attained. So each well-partial order has a longest possible extension, which is an ordinal. And you can sort of see, you can get an idea just by thinking about it, how the proof would begin. It would be some sort of transfinite induction, but there's a tricky step in the limit case. Essentially, you'll be presented with a whole bunch of linearizations of smaller well-partial orders with no clue how to put them together. And that's why it's an interesting proof, but no one will get into. Now, there was a slide a few slides ago that looked a lot like this. It was just saying that if there's a quasi-embedding from A to B, and B is a well-partial order, then A is as well. So here's kind of a strengthening of that result. We know not only that it's a well-partial order, but that the maximal order type is bounded by that of B. And the proof of that gets interesting too. But that, again, is not our theorem for today and not something we'll get into. And another thing that's similar to the previous slide is that these two constructors respect not only the fact that it's a well-partial ordering, but in fact the maximal order type as well. Now, I don't know if these symbols are familiar to you, so I'll just say that plus and times with the circle are the so-called natural sum and product. With, I'll give you one example of what it does. If you normally add omega squared plus 1 to omega, then the omega will gobble up the 1. But what the natural sum does is you gather the like terms based on these things as treating them like a polynomial and making them commute. Okay. Now, is there anything interesting we can say? Well, yeah, I'll draw that example again. If that's your A and that's your B, 2 copies of omega, and and you quasi-embed the one into the other by whichever method you prefer, then n of A is known to be less than that of B. And B is isomorphic to two omegas beside each other, which is omega times 2. So this is all pretty standard stuff. But I'm calling it basics for a reason, because we're going to build on that just a little bit. We're not going very deep into this stuff today. The problem with these well partial orders is that there are a lot of basics. So here's one last thing. It's called a left set. The left set of an element in well partial ordering, or any partial ordering really, is just the set of things that A is not below. Now, I've heard different theories as to why they're called left sets. Some people say because A is not to the left of B, or some people say because B could potentially be placed to the left of A. In a linearization, some people have told me because they're what's left behind when you remove some elements. But anyway, they're called left sets. And now I'm not sure why I left this empty space here. There was something I wanted to write, but anyway. Here's a theorem, an interesting theorem, which is that A is well partial ordered if and only if all of its left sets are well partial ordered as well. And that's, again, a one-line proof pretty much, but it's useful. A second quite interesting theorem relates these left sets to the maximal order types. And what it says is that A is basically the supremum of the left sets of its elements, or the supremum of the maximal order types of all the left sets. And then there's a +1 in here just to, well, if you think of a finite case for a 4-element well partial order, the maximum of these left sets would be 3. And in general, successor cases are like that. You just need to add 1. So here's something I'm going to put in quotation marks, because again, I don't know for sure that this proof is really new. Andreas has told me it is in some sense implicit in the thesis of Diana Schmidt, which I believe was from 1979. And it's totally possible that there are other versions of the proof in the literature that resemble this also. But the point is not that we're proving a new theorem anyway, it's that the way we're writing it is extensible, and what we're hoping to do, I've called this a work in progress already, is extend this method and get much more interesting things out of it. So let's see. The proof or the theorem is if A is a well partial order, then A star is well partial ordered. Okay. What is A star? It's equal or isomorphic, if you want, to this thing. A times x plus 1. Okay. By the previous slides theorems, what we need to show is that the left set of every string, call the strings x, is well partial order for every x. This is something we can do by induction. And we'll call it structural induction on the term, which is x. So that'll be two cases. I guess you would call this the base case. If it's a dead end, a leaf node, I should say, then Lx is empty. So that's a good case. It's empty because the leaf node embeds into every tree. On the other hand, if X is circle, or every string, I mean, if X is a circle, and then the first element of the string, then what is Lx? Well, by which I mean, what are the X prime satisfying this? So one example is if X prime is a dot. Because X is non-empty, it doesn't embed into the empty string. Good. Another possibility is that it also has a first element. Oh, there's a little typo here. Of course, the string has a first element and then a proper substring. These things are supposed to be well-founded. So the other possibility, if this second string is not empty, is that it has a first element and then the rest of the string. So for X not to embed in X prime, let's see. I mean, the possibilities will be either X1 does not embed into X prime, or A does not embed into A prime, and X does not embed into X1 prime. So this looks a little strange probably, but these two alternatives are just saying, if you try and match up the strings in a greedy algorithm fashion, either you can peel off the front, you can match up the first element of the two strings and throw them away. But then if you can't do that, then you would have to embed the whole string into the second substring. And the other case is maybe you can do that, maybe not, but we can't even embed the substrings into each other. So it doesn't even matter. So I'm going to be a bit hand wavy at this point. So L of X, is it a quasi-embedding? It is, but we're going to play a little fast and loose over whether these things are quasi-embeddings or some other kind of embedding. But the point is that Lx goes into dot or A cross left set of X. Well, we'll keep them in order. A cross left set of X1, the substring, or L of A cross left set of X. So here's the weird thing. Hold on, let me highlight this. I'm mapping Lx into something bigger containing Lx and calling it progress. And here's the reason. It's that this one is actually represented by X1 prime. If this was X prime, this thing is supposed to be X1 prime, lower complexity. And this is a place where you might find this hand wavy, but there are other ways of saying it, I'm sure. But the point is that we can then go into this one and do the same thing with it and sort of unroll a loop, so to speak. And so that's the really squiggly line. But when you unroll this loop, what you get is this, LA cross X plus A cross LX1 plus 1. Okay. And I'm leaving out sort of a step in this proof, but the point is that the maximal order type of LA is strictly less than the maximal order type of A. That's a consequence of a previously stated theorem. So that this thing is like a polynomial with ordinal values. And although this beta is bigger, this coefficient alpha is smaller than we started with. So we can perform some kind of induction on this. And I'm only being a little bit dishonest here because, of course, our theorem is about having a +1. And we haven't dealt with the case where instead of a single dot, we'll have an arbitrary beta set of labels for the endpoints instead of just a terminating character for the string. But that's the gist of it. And I would say that's the whole proof, if you don't mind eliding over that detail. It has to be a bit longer to accommodate this. And then if you want to make it a lot longer, I'll put a box for my admittedly a little hand-wavy proof. If you want to make it quite a bit longer, and this is part of the project that I would call ongoing, is that you can get a good analysis this way from these order types of the maximal order type of A. Ooh, I say MLA. Oh yeah, that's fine. The maximal order type of A using these X's. Because of this quasi-embedding means this is no greater than the maximal order type of T. We'll call it LA times X union the rest. But doing this properly and finding the right ordinal exactly requires a careful analysis of the Cantor normal form, and it gets annoying quickly. Anyway, the maximal order type of these objects is already known anyway. So let's see. Okay. And we're almost to the end. I'll show you another example like this more quickly. And then, yeah, old theorem 2. Now here's one that might also be familiar to people. So this is the binary trees with strong embedding that we introduced earlier. And that class is known to be a well partial order, and its maximal order type is known to be epsilon 0. And you'll see quickly that the proof of this theorem that I'm going to outline is actually a lot like the usual proof of this theorem, but it's in some ways more orderly in my opinion, less ad hoc. So what do I mean by that? Binary tree is this, x cross x plus 1. Okay, and we do the same thing. If x is the endpoint, or a leaf node, then its left set is empty. So there's nothing to prove. If X is not the leaf node, then it has two subtrees. And I'll skip the everything but the chase. The things it doesn't embed into are the leaf node tree, or if you write out the definition, it won't look quite like this, but this turns out to be fine after some application of De Morgan's laws or whatever. Too many kinds of X. I'll try and write it clearly. That. So X never embeds into either of the two subtrees of the thing it can't embed into. And then you can sort of break up the cases and see that you can write it this way if you want. And as before, the things that would live in here or in here, they're all still from LX, but they're of some kind of lower complexity. Just as terms. So you can reach into those and sort of unroll the loop. Equal is a bit of an exaggeration. I'll draw a squiggly arrow. And you get again, with a little more rearranging by isomorphism and De Morgan's laws or whatever. We can just put them both on one side times X. And here's that endpoint dot. So since this is well partial ordered, well, I suppose we can write one more line. We already know this is Higman ordering, or isomorphic to it. These things are by induction both well partial orders. We know we can construct a new one with the disjoint union and the Higman ordering too. And this is well partial ordered by Higman's lemma, the previous slide. So LX is well partial ordered. Furthermore, by induction, just on these, the maximal order types of the subtrees, left sets, is less than epsilon 0, meaning it's less than some stack of omegas. But then, using what could have been the ordinal analysis from the previous slide, if we'd put in a little more work, or perhaps a lot more work. This means maximal order type of LX1 union LX2 star is less than or equal to, I'll just say about omega to the omega to this one. And I say about because when you actually try to analyze the maximal order type of the Higman ordering, it breaks down into three cases, but the basic case is just omega to the omega to that. It's kind of a funny thing, actually. So the maximal order type of 1 star is omega, because that's just the natural numbers. If you put a 2, it's omega to the omega. If you put a 3, it's omega to the omega squared. It's kind of an unexpected progression. So yeah, actually finite numbers are one of the cases that needs the about here. But anyway, the usual proof of this theorem is essentially the same as this, but instead of using the T operator in this sort of organized way that's the same as the previous proof here with Figman's lemma, people will just jump straight to the Higman ordering. So this is interesting to me because it's a general method that works pretty much the same way every time for ternary trees and so on. So in this final slide, I will say something about the motivation for this work. It's a conjecture of Andreas's that people have been calling Weiermann's conjecture. Now, I hope I wrote this definition of theta correctly. Let me know if you see a mistake. But theta is this strange function that is defined in this not quite predicative way. It takes the least ordinal that's bigger than beta. Oops, I've already made a mistake. Where k beta is the maximal coefficient, so named. Of beta. So this theta is bigger than that. And for all alpha less than the actual value, that value has a maximal coefficient smaller than that of beta, then the image of alpha is strictly less than gamma. So gamma is somehow inaccessible by repeated applications of itself. It's a funny function, and it takes a lot of computations with it to get sort of an idea of how it works. But there's some interesting theorems you can prove with this function. And here are just a few examples. And this is also part of the reason I vacillate over how to write t, whether to put the dot here, or maybe you could write something like t dot of x to symbolize that to hide the dot and make it more aesthetic, or just t of x. But anyway, you get a lot of nice values of this function. And the conjecture of Andreas is that this always works. And there's space here because there's actually, we can do a little better. There's a theorem that's attributed, it's in Jeroen van der Meeren's thesis. A lot of you probably know Jeroen. But there's also a paper where Andreas and Michael Ratjian are co-authors of it. But the gist of it is this, that if you take trees and then this sort of B constructor of this, I hope I'm writing it correctly. Plus one. Oh, I should mention what this big omega is supposed to be. It's actually the same as omega 1. Just some people like to write it this way. So epsilon omega plus 1 is the first uncountable analog of epsilon 0. So why plus 1? Because it's pretty easy to see that epsilon big omega is just big omega. And so what the main thrust of this project, what we're trying to do is both prove this conjecture or a variety of a version of this conjecture, and also make it work when there are more t's. So here's maybe another way you could write these trees using notation that hasn't been defined, but the binary trees are themselves represented by a t, and then this external t makes the t here. So here's how the computation should go, with, again, functions I haven't defined. It should go like this. So if theta of omega squared is epsilon 0, then theta 1 of, omega 1 squared, which is omega 2 with the little omega, should be this value here. So the world should be nice, in other words. So if I may extend the conjecture a little bit, the world should also work nicely for multiple t. Anyway, I think that's all I wanted to say today. Again, these are partial results. We're not done yet, but I found what we've done quite interesting, and I hope you do too. Okay.
Okay, thank you very much for this very nice talk, David. So, does anyone have questions? Please unmute yourself and ask the question.
If I may.
Yes.
Yes. I wondered a little bit, your T operators resemble the functors in co-algebra. So I'm wondering whether you have investigated connections of what you're doing with co-algebraic approaches.
So by co-algebra, you mean like universal algebra, and then you turn the arrows around?
Yes.
Right? No,
it's more or less the idea. So you have also a concept of co-induction there. And your inductive proofs, again, have some flavor of being co-inductive rather than inductive.
No, we haven't considered co-induction at all in this project, but that sounds very interesting to me.
I'm not an expert, but I have a whole group in my institute working on co-algebra. So I recognize the patterns, but I'm not seeing whether it's a real fit or not. It's something you could consider.
I find it interesting that co-induction would resemble this, because to me it is just structural induction on the well-ordered part of what you construct this way, like a term algebra, an algebraic data type or whatever, or inductive data type. But
this definition basically says that the ingredient is embedded in some contrived construction containing itself, and that has a co-inductive flavor. And a lot of things like strings and trees and all that stuff has been included in co-algebra.
Okay, thank you. We might have to look into sort of the ill-founded part of this. I hadn't thought of that. Well, I guess we won't have a maximal order.
One other comment in your very first slide, I think there is a disturbing typo. The first one, yes. This the bad sequences. You have an A1, which presumably should be an AI.
Yes, that's definitely not how it's supposed to be.
So that's
Yeah,
bad typo then.
yeah.
Okay, thanks.
Okay, thank you very much. Is there any other question?
Yes. So can you go back to your slide on with the proof of Higmann's theorem? Just a small question. So I don't understand why on the bottom left it's not an and inside of the either or.
Actually, I wonder the same thing. Yes.
Could you repeat that?
So you give a condition for x not to being smaller than x prime, and if so, you have either x prime is a black dot, and in this case it's okay, or otherwise x prime is a white dot, and then it should be both x1 is not less than x1 prime, I think, or I might be wrong, but inside of your last either or, I don't understand why it's not and.
Yeah, well, let's take a look.
Yeah.
So what is this? Let's just look at them as strings. A sigma is less than B tau if, first of all, either A is below B and sigma goes into tau, or we can just ignore the first part. Sigma, A sigma goes into tau in the first place, so B didn't matter. Is this a correct sort of contrapositive of that?
Doesn't seem so.
Or negation of it? Okay.
I think the either or should be an and the and should be an or. I think by Morgan's law, right? Or maybe.
Yeah, I think just the either or should be changed to a and.
Oh well, I guess
Yeah, something weird is going on here.
Yeah, we can figure out like. I guess we just need to take like pen and paper and just think about it.
But I think it's just propositional logic, but
yes.
But I think that eventually, I mean, David was correct.
Oh, okay.
It's not just simply negating and taking just the negation. It's negating and then working a little bit more, and you get actually what is involved, I think.
Okay. Okay.
Okay.
Other questions?
Maybe I can give a general comment. So this whole investigation is a continuation of what Jeroen has done in his PhD thesis. And the plan was actually to work on a theorem by Harvey Friedman. And Harvey Friedman has studied tree embeddability with the so-called gap condition. And Jeroen was able to treat the cases with two labels, which was already complicated. The next step is to consider the case of an arbitrary finite number as the set of labels. And the final upshot would be there's a theorem by Igor Krish in Annals of Mathematics, where the labels are indexed by ordinals. But this is currently completely out of scope. So we are convinced that we are able to move Jeroen's stuff further to an arbitrary finite number of labels. But for ordinal labels, we don't know. And if somebody is interested in the thesis by Jeroen, we can supply a PDF. So it's from 2015.
Okay, thank you very much for the comments. So if there is no other question, I think we are going to close this session. So we can just, so thank you again, David, for your very nice talk. Let's just